One last thing I wanted to address on the specified flux condition is when we're going through and specifying the heat flux, we're solving for the mean fluid temperature. So let me just plot this out. So let's say we have a plot of a temperature profile as a function of position x. So here's x. This is temperature. And if I wanted to plot my mean fluid temperature as a function of position x, remember it's linear. So it might look something like this. Right? I have a mean fluid temperature as a function of position x. We're adding heat at a constant rate. The question I want to ask is, what if we want to solve for the surface temperature? Right? The surface temperature in terms of the position x. And by surface temperature, I mean like you have the internal flow, the mean fluid temperature, and then the surface between the fluid and the wall, right? The surface of the wall. So if we plotted that out, what is that going to look like? Well, remember now there's a developing region. So let me just kind of draw something here. So let's say at this point, this is x, f, d, t. This is the point at which flow becomes thermally fully developed. So at the very entrance of the pipe or duct or whatever, at the very far end of the green line there, let's call this here x equals 0. At that coordinate, how thick is the boundary layer? 0 thickness, right? It's just entering. So with a 0 thickness boundary layer, what's my heat transfer coefficient? Infinity. So if I have an infinite heat transfer coefficient, how is the surface temperature related to the mean fluid temperature? Anyone know? Infinite heat transfer coefficient, surface temperature relationship to mean fluid temperature. The same? Right. So they're the same. So I know, let me just draw it in blue here. I know that the surface temperature at this point has to be equal. Once I get to the fully developed point, that xfd, my boundary layer thickness stops changing. So at that point and beyond, the relationship between surface temperature and mean fluid temperature is that there's a constant offset, right? So it might look something like this. In that point, in that region in between, what's happening? Well, we're going from a boundary layer that's 0 thickness and it's growing to the point of being fully developed. So there's like a smooth transition. So the surface temperature is going to look something like this. So this is our Ts, this is our Tm, and they're both a function of x. So hopefully that makes sense. In terms of the math that goes into this, all we're really saying is that Ts, the surface temperature, is equal to the mean fluid temperature Tm plus, let's say, the heat flux Q dot double prime divided by the local heat transfer coefficient. Right, this is just an energy balance kind of flipped around and solved for the surface temperature. Right? So that's kind of where I wanted to wrap up on the specified heat flux. Now let's talk about the specified surface temperature model. So before I move on, any questions on that? That's a really good question. So in this situation, the mean fluid temperature is changing. So there's sort of this, how do you describe it? I guess the rate of change is sort of constant. So things sort of come to this kind of quasi-equilibrium, even though the temperature continues to change. So the fact that temperature is changing is important, but it's not as important as what's happening when that boundary layer is still changing its thickness. So, and that's like a more significant effect when you're going from like uniform free stream temperature to just like what's happening right at the entrance where there's that viscous boundary layer that's also developing. So is it really the case that this is like fully developed in the true sense? I guess not really. Like there's still an effect that comes from the mean fluid temperature changing along with the surface temperature, but that's less important than that entrance region. All right. It's a good question. It's just kind of a subtle thing. Anything else on this? Okay. All right, let's move on to the specified surface temperature. And what we're going to do here is we're just going to kind of walk through another energy balance, and I just want to show you how the solution changes. So by solution, this is a solution for mean fluid temperature as a function of position x. We derived it, it's a linear expression. So if we now substitute our assumption that we have constant flux with a substitution for constant temperature, how does this change? So let's go down here, and I'm just going to kind of write the starting point.